Okay, this is for dynamics, the step 8 for the project. So basically, how I went about solving it is, um, so basically the drag is going to be a function of velocity, and then you have mass times gravity pulling down. Basically, you reach terminal velocity when these two become equal, still moving at a constant velocity, but the acceleration is zero at terminal velocity, so basically stops accelerating. So basically, I just subbed in acceleration, which is equal to dv dt, and then the force is going to be the difference in force between drag and gravity. So you just move these around. Difference in time is going to be equal to this, which you're going to integrate with respect to v, and then that will give you the and then integrating dt on the left will give you the time. So time equals all of that, which I just used to solve for how long it would take to reach terminal velocity. And then solving for terminal velocity, I just used, where did I put it? I know I had a picture of it somewhere. It's the square root of 2gm. Oh, where is that? Yeah, that's right here. It's the square root of 2mg over the drag constant times the air density times the area in contact with the air. So I basically used that to solve for the terminal velocity. As far as this goes, I actually ended up just solving for velocity. So I solved for velocity, and then I actually just integrated this again to give me the position, because position is the integral velocity. Velocity is the derivative of position. So I actually just changed the v to dy dt, which is, the y distance. So yeah, I solve for the dy and then the dt on the right side. So it's going to be a position function based on, it's a function of time that gives you the position. So you integrate this again. I'm going to be honest, I had to look up how to do this integral. I had absolutely no idea how to integrate that. So yeah, it gives you that for the position. And then from there, I can show you some of the examples on how I went about solving it. So yeah, so I solved for the final velocity here, 28.5 meters a second. I just plug in everything into the time equation, which is this one. So I just plugged in the mass. This b, so like I said, the velocity is a function, the force is a function of velocity. So the faster it goes, the more force is acting on the object. So instead of plugging in the whole 1/2 rho c a v squared, I actually just used the slope from the graphs that I made last time. So this is the slope of the force based on the velocity of the air. So I just use that for the b, because the force basically just scales linearly. It doesn't really, but we just use a line fits here. So basically just scales linearly with velocity. So as the velocity increases, the force is going to increase. So I just used the slope for b as far as that goes. So I just wrote all these down like this. So we had the mass, we have the slope from the graph, which is basically scaling our force based on velocity, because we calculated that last time. Solve for the terminal velocity, just using the 2mg over rho a c, the drag constant. And then we just plug in everything here. So this is basically just that equation right there. Plug in everything with the terminal velocity that we found, and that's going to give us the time. And then for the position, we need this time because this position function is a function of time, which is that equation right there. So we just plug everything in again, but instead of plugging in velocity, we're just plugging in the time that we found. And that will basically give you the distance that it fell. It is negative. I just wrote it here as positive because it's going, in the negative y direction. So that's how I solved those and I went through and did it for all of them. So the sphere, golf ball, cylinders, and then for the last part, calculating how long it will take to get to a percent of the terminal velocity. So like 50%. It's not going to be half because this equation is definitely not linear. Using natural logs, it's using e exponentials, so we can expect it to be more or less, most likely less, as far as the time to get to 50% of its terminal velocity. So yeah, basically what I did is I just calculated 50% of the terminal velocity, plugged everything in again to get a new time, and then I just plugged that time in into the position one again to just find this. So when you think about it, I mean, this actually makes sense. The time is going to be a little less than half because the force slowing it down basically increases the faster you go. So it's going to take longer and longer to reach that terminal velocity as you go along. So this makes sense that it's less than half. Same with the distance. You're not moving as fast because you're accelerating downwards the same direction as you're moving. So you can expect less distance to be traveled the first half than the latter half reaching your terminal velocity. So that's how I went around solving those and everything. I believe this is correct and everything. I'll upload these pieces of paper. But yeah, that's how I went about solving it. The results made sense. Functions also made sense. So yeah, thanks for watching.